As a Node.js application scales, its plugin architecture almost always hits a fatal ceiling. You build a clean, modular system, but eventually the sheer weight of interdependencies causes the structure to collapse. The root of this collapse comes down to a conflict between two dimensions. First, you have to isolate a plugin's state, the space problem. Second, you have to manage when that plugin loads and unloads, the time problem. Try to manage both at scale, and you inevitably end up with a spaghetti architecture. Shared data leaks across boundaries, and race conditions plague the system during startup. Standard dependency injection is the usual band-aid here, but DI is entirely insufficient when your architecture requires you to manipulate modules dynamically at runtime. When dependency injection fails mid-execution, the symptoms are severe. You get silent state leaks that corrupt data, and hot module replacement triggers fatal crashes that take down the entire host process. Historically, the Node ecosystem has treated dependency tracking and lifecycle hooks as completely separate engineering domains, leaving developers to write custom glue code to bridge the gap. Scaling modern applications is bottlenecked precisely by this unaddressed, two-dimensional architectural conflict. This is the Cordis GitHub repository. It's an architecture explicitly engineered to solve this intersection, branded as a meta-framework of spatio-temporal composability. That term sounds dense, but it has a strict mathematical definition. Spatio-temporal composability is the exact alignment of isolated context boundaries with dynamic component lifecycles. Cordis is not a standard application framework like Express or Nest. It is a meta-framework. Its entire utility is abstracting the foundational logic of plugin management. It exists so framework authors can build complex module systems without reinventing lifecycle management from scratch. By unifying the spatial and temporal dimensions into one system, Cordis absorbs the dependency plumbing. Developers building on top of it only have to write their business logic. It provides the absolute bedrock for highly dynamic, state-safe software architecture. This 2D coordinate plane maps out the framework's mechanics. We plot temporal composability on the x-axis and spatial composability on the y-axis. Let's look strictly at the y-axis, the spatial dimension. This represents how the framework isolates contexts and manages dependencies internally. We see this spatial rigidity in the commit history. A core update removed optional injection semantics. This enforces rigid boundaries. A dependency either exists in a given context or it doesn't. There is no gray area for state to leak through. A plugin's context must be structurally deterministic. That is the absolute only way to guarantee that one module's memory footprint never bleeds into a neighbor's. We see this enforced down to the smallest utilities. Another core fix ensures the system logger strictly respects definition site names. True spatial awareness requires everything to inherit the exact context of where it was defined. The logger can't just guess where it belongs. It is permanently bound to its parent context block. These constraints ensure that every module exists within a predictable, verifiable location in the dependency graph, preventing the runtime entropy that typically degrades large-scale applications. This timeline on the x-axis represents the temporal dimension, the state of the system as it moves through load, init, update, and destroy phases. Moving a system through these lifecycle phases is straightforward until you hit the update phase. Mutating state while a system is actively running is where most architectures break apart. Cordis is heavily focused on this exact problem, evidenced by core commits enhancing external detection for hot module replacement. Hot module replacement is the ultimate punishing stress test of temporal composability. Traditional architectures fail this test because they cannot safely sever a running plugin from the dependency tree. To change one piece of code, you have to restart the entire node process. Cordis manages to gracefully degrade the context. It safely unloads dependencies and swaps the module mid-lifecycle, leaving the rest of the running system completely undisturbed. True temporal composability means the timeline can be manipulated programmatically without ever triggering a fatal crash. Managing isolated space is one challenge. Calculating how those boundaries interact with a shifting timeline is another. This grid visualizes that intersection. You need a mechanism that tracks every data flow at exact coordinates on the plane. The solution lies in the explicit inclusion of the effect pattern, which is listed as a primary topic tag in the Cordis repository. Algebraic effects are a programming pattern used to isolate side effects from core business logic, preventing unpredictable state mutations during execution. In this architecture, effect-driven patterns act as the underlying physics engine for the framework. This engine allows active plugins to be injected, paused, or cleanly discarded at any precise coordinate of space and time. The effect system is the critical mathematical bridge bringing spatio-temporal composability out of academic theory and into a production-ready runtime. Zooming out from the 2D grid, we can see the real-world ecosystem built on top of this architecture. It is easy to look at this level of strict mathematical rigor and dismiss it as over-engineered for a JavaScript runtime. But the repository currently shows 350 dependent projects in production, proving mass adoption of the pattern. Cordis itself does not build the end-user application. It builds the robust floor that other frameworks stand on. This abstraction grants downstream authors immense velocity. They can build rich plugin ecosystems without having to architect complex hot module replacement infrastructure from scratch. Abstract architectural rigor at the root level directly translates to exponential developer velocity at the surface level. As the TypeScript and Node.js ecosystems continue to scale, developers are hitting the limits of traditional structures, demanding these more advanced paradigms. Spatio-temporal composability provides a highly rigorous framework for building modular systems that remain completely stable under frequent runtime changes. Understanding the interplay between context boundaries and life cycles allows for the construction of systems that are resilient to the side effects of hot-swapping code. The formal mathematical proofs driving this entire architecture are available in the repository's linked white paper, titled A Programming Paradigm for Spatio-Temporal Composability. The path toward more scalable architecture relies on frameworks that manage both the isolation of data and the dynamics of its lifecycle within a single unified model.